we are ready, yeah, then good. Then I continue, yeah? All right, good. So, welcome back. During the break, I heard already that maybe one could expand and show you more different things than what I have. So if there's later on interest, I have so many different slides and subjects to show. You could always ask me something and I could put it together for tomorrow or so. I heard you would like to hear a bit more about non-metallic materials. I have nice examples on that. I could always bring together something. For the moment, it's all on metals, but I have beautiful other results as well. So, so far, we have seen what eBSD in general can do. And now I would like to show a little bit shortly how actually eBSD are formed. Very briefly, we are still in an introduction, and what we can do with this knowledge particularly. Yeah, and so let me start. Okay, the most important thing is I will make a little difference for you between kinematic and dynamic diffraction theory. I will not go into details because this is too difficult for a short moment, for this short lecture here, but I just want to point out that is the major important difference which I will talk about. And I will start with the kinematical theory, which you could also call the geometrical theory of eBSD. All of you know the Bragg equation. And the Bragg equation is in principle a very geometrical understanding of diffraction. Yeah? You assume the electrons, I don't know whether I have it here. Let me shortly switch to a different presentation. Verwerfen. Where is it? Yes. Yes, exactly, this one here. So, the Bragg diffraction is, I'm almost certain, I need my glasses, is well known to all of you. And it's just a very simple approach to diffraction, actually. You say, I have scatterers, in our case the atoms. I have a wave which is coming in, which enables these electrons or these atoms to scatter these incoming waves. And actually what they are doing is every arriving electron wave is actually exciting new elementary waves from every atom. Yeah? So you get actually every atom starts oscillating and emits new electron waves or new X-ray waves. And all these X-ray, or in this case electron waves, superimpose. So this is actually just pure geometry. I just have drawn circles. Yeah? I don't do any complicated Schrödinger equation solution, nothing. It's just pure geometry. And I let these elementary wavelets overlay. And actually, if I look, where do these wavelets overlay? I find in certain directions they are overlaying. I could make the same nice drawing with waves on the beach. You would get the same beautiful picture. Maybe later on I show you my latest animation on that. But anyway, for the moment, I just don't talk about my great animations, but just about Bragg equation. As a result is, you're finding that under certain angles, only under certain angles, which are called the Bragg angle, you're getting superimposition of the waves, and you're getting not only reflection, but you get reflection only under the Bragg angle. And you all know that this is then the Bragg equation is fulfilled, n times lambda equal 2d sinus theta, the Bragg equation, and there's pure geometry. There's no big science behind it. Once at Bragg's time, it was big science, but nowadays we understand this is simple. Yeah, and eBSD you can understand in this simple manner, purely geometric, and you will see that this is not sufficient, or that leads to sufficient understanding for the beginning, but not for later. And now we are later already. Yeah? So you remember this was our setup. We have a steeply tilted sample. Electron beam falls onto that. Something happens with the electrons, and then an electron diffraction pattern is observed on a camera. And this electron diffraction pattern looks in principle like that. Okay, so I showed you already we have these beautiful bright bands crossing everywhere on the screen, and these bands consist of Actually, usually you have a bright band and two black lines at the side. Yeah? And sometimes you have the situation that you have a white line and a black line on either side. These lines are called Kikuchi lines. These bands are called Kikuchi bands. Good. So this is just how a pattern looks like. And now, where is the Bragg equation in there? And that's what we figure out now. So let's look how these patterns are in principle formed by a very simple geometric understanding. So this is one set of lattice planes in a crystal, and we let an electron beam fall onto these lattice planes. And very important is, this crystal must be large enough to allow the electrons to spread out. When you do TEM, you don't want the electrons to be spread out. You want the electrons to be following particularly exactly the same straight path of the incoming beam through the lattice, and then you will get the spot diffraction patterns in TEM. But here, you don't want that. You want the electron beam first to be scattered incoherently in all possible directions of space. So we will create a little scattering volume, which is a few 100 nanometer large maybe, or sometimes only a few 10 nanometer large. And in this volume, electrons travel in all directions. So they are no longer following the primary beam direction. They have lost any coherence with the primary beam. That's very important. They have not lost their energy, so they are still having their original energy, for example, 20 keV. They have not lost that, but they have lost the direction and the phase relationship. That's very important. And later on, we'll come to that in more details. Now, once again, it's just intuitive understanding. And now, out of these many electrons which are traveling in all directions, you select those which, by chance, hit on these lattice planes by the Bragg angle. Yeah, so you look on all these electrons, which of them are hitting the planes at the Bragg angle. And these ones will lead to diffraction, as I showed you before. Very simple. And you look, what is the geometrical locus of all these electrons? And you find, aha, it's actually these big cones here. All these cones, the electrons have so if the electrons travel on these cones, they all have the same angle with the lattice planes, actually the Bragg angle. Yeah. Good. So we find that these two cones, one forward and one backward cone, are the areas where electrons travel under the Bragg angle with respect to these lattice planes. And now, in order to do EBSD, we are tilting the whole setup. So instead of looking in transmission, we are looking in reflection. So still the same thing. The lattice plane, the crystals has been changed now, and the cones are now traveling in this direction. And actually, what you see here, these cones, I mentioned these cones are traveling under the Bragg angle, and in electron diffraction, the Bragg angle is very small in normal electron diffraction. The Bragg angle is only in the order of 1 degree or 2. So these cones here are almost perfectly flat. They have almost no opening angle. Yeah, it's almost a flat plane, and that's why when you place a detector here, you will find that these cones here are almost making straight lines. They are not really straight lines. They are slightly curved because it's cones which are cutting the detector, but almost straight lines. And if you look back here into these pictures here, you actually see that it is not perfectly straight lines. For example, this band here, it's a bit wider here than it is here. Yeah? So you see, it's actually slightly curved. It's a hyperbolic cut through, it's a conical cut and making actually a hyperbola. With respect to the screen. All of these lines have a slight hyperbolic shape. Yeah? But for time being, we can assume that it's almost perfectly straight. And actually very nice is, so these are these two cones. Actually, this is one side of the band and the other side of the band. So this is making one cone and the other cone. And something should come more. That's a shortcutted image. In principle, if you take these planes here and extend them all the way to the phosphor screen, then you would find the position of the plane makes approximately the middle line between these two Kikuchi bands, yeah? Between the two Kikuchi lines, sorry. So the geometry is very, very simple of EBSD. Yeah? In principle, each of these bands is just a projection of the lattice planes onto the phosphor screen. And as we have many different lattice planes in a crystal, yeah, infinitively many in principle, we get all this set of of projections of these, gnomonic projections of these lattice planes. So, and the Bragg angle is actually just the opening angle from one line to the other line here. So that's the Bragg angle. That's where Bragg plays a role, and the rest is just pure geometry. Just take the planes, project them onto the screen, and there you are. So in principle, very simple. But now, and with this, every one of you can write its own computer program to plot an EBSD pattern on the screen. Yeah? This is geometry is 10 lines of code. No? So it's not so complicated. But now if you pay well attention to my speaking, then you would expect now that here is intensity of these Kikuchi lines, and everything else should be, everything else should be black. Yeah? So we would expect two bright lines running over the phosphor screen, and the rest should be should be dark. We see the opposite. We see actually that we see two black lines running over the phosphor screen, and the rest is bright. And even in between the Kikuchi lines, it's even brighter. Yeah? So, and this you cannot explain by the kinematical theory. It's impossible. Yeah? There is no way to say from simple geometry why the energy distribution or the intensity distribution is like that. Why are the Kikuchi lines black and the Kikuchi bands in between are bright? And for this you need, unfortunately, to solve the Schrödinger equation. That means you need to go to the physics of interaction of electrons with matter, and not only the simple geometric picture. So we are leaving the kinematical theory and we are coming to what is called the dynamic theory of electron diffraction. And I don't show you this in detail now. We can do it if you like tomorrow, if we talk, or even this afternoon. Let's see do you like to stay here until 8 o'clock? Then I would about reach it. I hope you don't say yes. Okay, good. No, that was of course a joke. But we could talk about this in more detail. What you need to do is you solve the Schrödinger equation for a high energy electron, that means a 30 keV electron traveling in a regular crystal lattice. And this is in principle what you need to solve. We are searching the solutions for the electron wave function inside of the crystal. Where does it go? Yeah? We don't need to understand that. It's in principle only an energy summation of electrons inside the crystal and outside of the crystal. And there is a solution to this beautiful equation, which is given by Bloch waves. So it's actually only solving a partial differential equation. So Mr. Bloch had the idea, I can solve it by selecting individual wavelets and making a sum of these wavelets, and these wavelets will actually give a solution to this equation. There's a lot of myths and misunderstanding about Bloch waves. I will not come to this today, but if you like, we can speak about it later, or when I'm coming again another year, then I will speak about Bloch wave theory, which I like because it's often misunderstood, the Bloch wave theory. But anyway, this is just a mathematical solution to the Schrödinger equation. The Bloch waves have no physical existence, they have only a mathematical existence. And often you read in papers, the Bloch waves are traveling this way and that way. This is not true, there is no Bloch wave existing. There's only one wave, and this wave is solving the Schrödinger equation, and just the Bloch waves allow us to solve that. But okay, if we are now solving this, we are using Bloch waves, and we can get to a solution of this wave function, and then we can tell actually how much electrons are scattering in which direction. Okay, this is just mathematics. If you are able to solve partial differential equations, you can follow that this line here. That's a bit too short for following it, but you can in principle find it in textbooks. And what you then do is you plot, okay, you get an explanation of the electron intensity independence of a factor or of a variable W. And this W is called the, how is it called? Let me think. Is there a number of the, yeah, exactly. We call it the deviation parameter, W, Bragg deviation parameter. It tells us in principle which intensity do we get depending on how far away I am from the exact Bragg position. Bragg position means W equals 0. So then the wave's traveling exactly in Bragg angle, and if I'm different angle, then W has a value, either positive or negative. And I can solve this equation here. Here is the W, and I get the intensity. And if I solve that and plot it, then I get this picture here. Here is this deviation parameter W from 0 all the way to 3. And I calculate that, and I find, okay, if we are very close to the Bragg condition, then this solution of the Schrödinger equation shows me that we are getting almost no intensity back. Yeah? So there's actually almost no scattering getting through when we are almost precisely at the Bragg angle. That means we see a black line where we should intuitively think it's a bright line. Yeah? And quite in contrary, when we're getting closer to the lattice plane, so the W becomes negative, then we are getting high intensity. We have a dark line, high intensity, and then we are switching over to the backside of the crystal lattice planes, high intensity, dark line, and normal intensity again. So and we have seen that already. Where is it? In our diffraction patterns. So we see this Kikuchi band here. It has a bright center, which corresponds to this bright area, and it has two dark sides, which correspond to these two dark sides here. No? So, and if we plot the intensity distribution across this band here, we find something which is relatively close to theory. This is a very simple theory here, which I gave you here. It's only two beams considered, only one lattice plane, and only two beams considered. Then we come to a very simple equation, which I can write still here. If I take a real Kikuchi pattern, so for example, overlapping of many crystal planes, all giving diffraction, then I cannot write down the equation any longer. Then only the computer can solve it iteratively. The Schrödinger equation solution will then become quite complex, but still any computer can do it, yeah, if you once have the software for it. Okay, so this is just the basic theory. We call this dynamic theory, and the dynamic theory tells us there is no bright Kikuchi line, but a dark Kikuchi line, and there is a bright Kikuchi band. Okay, and now we write software which allows us to calculate that. And we write software, I mean Eimo Winkelmann writes software, yeah. I haven't done that. I have only done the solution for the two-beam case, but Eimo Winkelmann has, in the last 10 years, written code which allows to simulate these diffraction patterns with all the intensity details which you can imagine. And okay, nice exercise, academic, go away, yeah? No, and you will see now this is not a nice exercise, this is extremely powerful to do that. And this is, in my eyes, the future of EBSD use, yeah? Besides, of course, measuring microstructures, but this is really powerful. So let me show you why. So we have here a diffraction pattern of a Lavus phase. Lavus phase is this crystal structure here. C14 Lavus phase has one atom of one sort, A, and two atoms of sort B, and they are arranged in a particular crystallographic manner. And there is many different Lavus phases. Almost all metals can make with each other Lavus phases. And it is often a question, which kind of Lavus phase do I see there? And properties is particular and so on. So I took this diffraction pattern. I admit it's not the most beautiful one, but accept it for the moment. And I calculated the prototype of the Lavus phase, of the C14 Lavus phase, which is magnesium zinc. This is the prototype which you find in the international tables. I used 2048 different lattice planes to calculate using the software calculating it. And then I compare. And if you compare, you will find, in terms of geometry, everything is correct. The lines here are all at the correct place with respect to this one. But if you are now looking for a while, you say, but this does not look as if it fits. Yeah? For example, here, this center line should be white in the center and have then a bright diffuse band, but it's not white, and it has black sharp bands. And many other places I could show you in this pattern where it doesn't fit. So you think, this software is not good, not to say anything worse than that. No, but it's not the software which is not good, but it's my assumption that it's magnesium zinc which is not good. This is tantalum, tantalum chromium Lavus phase. So, and if you now enter the correct atoms here, tantalum and chromium, and calculate again, you see how strongly this changes. Geometry is exactly the same thing. I didn't change anything on the geometry. Yeah? I just changed the correct atoms. And you see now suddenly there is exactly this bright band in the center with the diffuse band around, and all the details which you have in this not so nice pattern are correctly reproduced. This is showing the power of this approach. Yeah? And what can we do? We could now do, for example, figuring out which kind of exact atomic occupation do we have by trying out. Yeah? We could modify the atomic positions. We could say, okay, probably there's one manganese there. Let's see how it influences this pattern and compare and then calculate for more and more until we have the right occupation of the lattice. This is still future, but I think this will come sooner or later. Yeah? That we can really do what you do nowadays you do in X-ray diffraction. You will be able to do on very small phases also with eBSD by just modifying the atomic lattice and seeing what is the outcome of the dynamic reflection, of the dynamic calculation. Of course, currently it's still slow. It needs 1.5 hours to calculate these patterns, but we're speeding up, or Eimo Winkelmann is speeding up that process. And Eimo Winkelmann and his good partner, Gerd Nolze, they presented a lot of beautiful applications of this new theory. I have also used it as you saw it, but I would like to go back to their work and show you one, for me, very striking example. They have presented many others, but this is a beautiful example about diffraction or microstructure analysis of gallium phosphide. Gallium phosphide is actually cubic, simple crystallographic structure, but it has no center of symmetry. So most of you are metallurgists, so you are familiar with FCC, BCC, HCP, and so on. All these metals have a center of symmetry in their crystallographic structures. But this one is zinc blende. The group is F bar 4 3M, and this is actually without a center of symmetry. And that means if you're looking into 111 direction, or you look into minus, oh wait, what is that? I need to find out where. Yeah, we'll see that. If you look in 111 direction or in minus 111 direction, the things look different. This is not the case in FCC, for example. Okay, so, and the material has important applications for optoelectronics, and it's for these applications very important whether you are looking in this one direction or in this direction, whether you first hit a phosphorus and then a gallium, right, or whether you first hit the gallium and then the phosphorus. This influences the optoelectronics very significantly. So is eBSD able to separate whether we have 111 or minus 111? And good, that is shown here. This is a typical diffraction pattern obtained from it, from this material. And now the question is, can eBSD separate whether we are looking, so this is actually, now I need to think, yes, exactly. This is a diffraction pattern simulated for the case that we are looking into minus 1, minus 1, minus 1 direction. And this is a diffraction pattern for the case that we are looking into plus 1, plus 1, plus 1 direction. This one here. So, and you see it already here. Here we are seeing only the green atoms, and here we see also the red atoms. So we are looking in different directions of the crystal. And if you look for a while, you say, this pattern and this pattern is exactly identical. There's no difference. And indeed, the computer also says like that. Yeah? And the computer, when you then map over a microstructure, the computer cannot distinguish is this or this, and it just gives you blue and red solution randomly. So you see there is crystals, but you don't get the solution, which direction is it. So there is no possibility to distinguish between these two phases. No, I wouldn't make this story if there would not be a solution to it. And actually now you have to look very carefully. You have to look into these diffraction patterns in more details. For example, you take this band here. This band, which is here in the experimental, and it's here in the two calculated ones. And now, if you have sufficiently good eyes, you will see that the white part is a little bit on the top of the band, while here the white part is a little bit on the bottom. And there is another line, this line here. The white line is a little bit to the left, and here it's a little bit to the right. Yeah, and actually I have plotted that with more details, and you find the same thing in the experimental pattern. So actually it's here, the white thing is a little bit to the bottom, and the white thing here is a little bit to the right. So this is indicated by these arrows here. And now let's look which one fits to that. So white to the bottom, and white to the right, white to the right. So this solution, this pattern here is actually correct with this solution here. and not with this one. So that's actually, do I mark it? Oh yes, here I show. This is inverted with respect to this, and this is exactly the right one. And now the software actually calculated these diffraction patterns and compares them with this one, pixel by pixel, intensity by intensity, and figures out that this one here fits better to this than this one. They both fit, but this one fits in intensity better. And the software does this now for every point, and then as a result, it is able to suddenly show the microstructure correctly separated for plus and minus. Yeah? And this is a very, how should I say, a powerful example, because in this case it really matters. Yeah, and maybe some of you have worked on zinc blender structures. Many solar cell materials, many optoelectronic materials are all zinc blender, and also of course in nature. And in the solar cell materials the polarity matters very much, and for optoelectronics. So this opens a new world for all these materials which have no center of symmetry to be able to distinguish that, yeah, with using a particular form of software, which is not only looking for where are the lines, but also what is the distribution of intensity of these lines. So that's hopefully showing you sufficiently how powerful this can be for modern materials. It doesn't matter for steel, it doesn't matter, although even for steel it may matter, but we'll talk about that another time. But it matters particularly when you're looking into functional materials. Good, and okay, that's in principle. I have spoken about that. We skip that now. Good, this was my little excursion towards the physics of it, and I'm happy to extend that further. Now we say, okay, we come back to conventional classical EBSD, and we measure misorientations. We measure orientations first. I will show you later how we do, and I will also show you later what are misorientations. There is lots of things to know, which I will skip over now, but I will just show you an application of it. Yeah? So if you are able to measure misorientations, means changes of orientations from one crystal to the other, what can you do with it? Is it relevant? Yes, it is. And it's relevant for many, many things, and I just have selected two. There is one subchapter is missing. And the first one is austenite reconstruction from martensite. So you all know, I believe, the iron-carbon phase diagram, and we're keeping it simple for the moment. We're just saying the major thing in the iron-carbon phase diagram, in the simple iron-carbon phase diagram, is that there is a high-temperature structure, which is called austenite, and it has FCC structure, and there is a low-temperature structure, which is called ferrite, and it has a BCC structure. And actually, they are very, how should I say, inversely behaving phases. Yeah, quite amazing. So this one here has high solubility for carbon, but low diffusivity for carbon, and high ductility, while this one here has low solubility for carbon, high diffusivity for carbon, and low ductility. Yeah? And there is more inverse behavior, but let's keep it for that. For the moment, a lot of this has to do with magnetic transitions between high and low temperature. Actually, it has a lot to do with the distance between the atoms. But okay, we will not talk about that now here. I just want to mention steel, and that's why a steel institute exists. Yeah? There is a Max Planck Institute for steel research or for iron research. There is no Max Planck Institute for aluminium research, and no for, let's say, magnesium research or so. It's because this transitions here makes steel such a complex and versatile material. Yeah? And by heating a material up to austenite and then cooling it down in a particular way, I will have more examples later, you can create all kinds of complicated structures. And you can create all kinds of complicated phase transformations. You have a ferritic, you have a diffusive phase transformation, which leads to just standard ferrite, but you have a bainitic transformation, and you have a martensitic transformation, so displacive transformation. All this depends on these different properties of these two phases. And the interplay between these phases creates an incredible amount of things which you would like to understand. So, and one thing is, of course, you know, the transformation from here to here. When you cool down quickly, you get a martensitic transformation. Yeah? And this martensitic transformation means the carbon diffusion will not happen, the material, the austenite will just transform in a crystallographic manner into the BCC, into the martensite. And this happens always when you take or often at least, when you take a high temperature austenite and you quickly cool it down. And what happens then is actually the following thing. This is the FCC structure here, FCC high temperature structure. And now inside of the FCC structure, you see already the BCC structure. It's actually here, marked in blue. Yeah? It's not yet BCC because it's still tetragonally extended. But in principle, inside of austenite, there is already the ferrite atomic arrangement. And now in order to actually get a ferrite, you don't need any diffusion. You just need to make this transformation and then compress the ferrite a little bit, or the BCC, the tetragonal lattice a little bit, and you come to the cubic lattice. So this is in principle when you do a quick cooling from high temperature to low temperature, it's just this. It just shrinks together. But what happens then when it shrinks from there to there? The atoms of the FCC and the BCC don't fit together any longer. Yeah, they don't have a proper relationship, so this cannot be the proper mechanism. What needs to happen, so these are the two lattices. What needs to happen can be shown nicely in this circle here. You have the austenite being displaced as a cube, as a sphere. And this austenite sphere needs to be compressed into a ferrite sphere. Yeah? And of course, when you just compress this, you will get actually, you make an ellipsoidal distortion. And the atoms, which are indicated here, the atomic or crystal positions indicated here by these red arrows and the blue arrows, they don't fit together any longer. So in order to make them fitting together, you need to rotate one of these lattices so that at least one of the two arrows fit together. You have an invariant line, and the others then are not fitting together. But what you can calculate is you need a 9-degree rotation of the crystal lattice of austenite to fit well in certain directions with the crystal lattice of BCC. And that means, so you first have this compression and then a 9-degree rotation, and that means you get an orientation relationship between this one and this one, which is actually in this particular case called the Kurdyumov-Sachs orientation relationship. It's this 9-degree rotation about certain axes. This is all you need to know for the moment. And if you know that, there's other relationships which you can also calculate and display like that, but for the moment just keep it with this. And now you can say, okay, we have here a martensite structure, and I would like to know, so let's put grain boundaries in here. This was measured with EBSD. You see all these fine lamella of martensite. Once again, I will have later on more detailed graphs on that. And I want to know which of these martensite crystals came out of a single austenite crystal. And for this, I now use the knowledge that there is this Kurdyumov-Sachs orientation relationship. All the martensites should be 9-degree rotated with respect to the original austenite. Yeah? And now I'm searching which martensite grains in here fit by 9-degree around certain axes to one common orientation of the original austenite. And this is done by another beautiful computer program, ARPGE, created by Cyril Caron. And this software just looks through this microstructure and looks for these relationships. And then actually what it does, it finds these. Yeah? And actually it regroups martensite, which all fit to the same austenite. And once again, this was a martensite. You don't see that there are grains inside. Yeah? At least if you have no prior knowledge, you don't see that. But if you now let the software go over it, you find, aha, there's a beautiful reconstruction into different grains. And these grains are, of course, much bigger than the martensite. And you see now they are more or less globular. They are roundish, and you can see how big they are and how they are arranged. So you can't measure that with EBSD because this was at high temperature during hot rolling. Yeah? And what you see with EBSD is this. And what you then want to know, what was it during the hot rolling cycle? So you get this beautiful structure, and you can now make all kinds of understanding of what happened directly before the material cooled down. Yeah? Very nice. That is one application, and for this you need to know whether it's Kurdyumov-Sachs or Nishiyama-Wasserman or Greninger-Troiano, this orientation relationship. But then once you have put it in, you can understand more. You can also use you can also search for the orientation relationship, yeah, and you find out, it's more Ks or more Nw, or it's more something completely different. And from this, you understand more how the material actually transforms, yeah. And one very practical example is the following. We were looking for fracture, formation of cracks in DP steels. DP steels consist just of, do I explain that? Yes, of ferrite, these gray grains, and martensite grains. And we find actually, so islands of martensite in a matrix of ferrite. And we find that, where is it? Here. If you look into one of these martensite lamella a little bit more in detail, after a little strain experiment, you find it cracks inside of these martensite islands. The steel always cracks there, yeah, and it starts cracking already at 5% of strain. It still supports then straining until 30%. But if we would understand better where the cracks form and why they form, we could make perhaps a DP steel much better, yeah, much more fracture resistant. So we looked into the marten, so this is the martensite here. I just don't show the ferrite which is around here. And you see again all the martensite lamella in here. And we reconstructed using the software where is the austenite, and we found, in between the crack here is always separating two different original austenite grains. Always. We never find a different case. It's never going right through an austenite grain. It always cracks along a grain boundary of two original austenite grain boundaries which were there at high temperature, which you don't see any longer here. And there was a whole PhD thesis on that, showing and explaining why it cracks along austenite grain boundaries. By the way, we did a lot of atom probe as well there. Fadi Archi's work, it was a very beautiful work showing the reason why these materials fail at prior austenite grain boundaries. And you see this can be done very nicely using the misorientation calculation inside of the martensite. All right. Another example now, okay, now we're coming anyway to, it's not the slide which I expected, but we're coming to property calculation, another application of misorientations. A bit more complicated perhaps. And for that is, we need to look into dislocations now for the first time. And actually, we need to look a little bit into classification of dislocations. There's actually, when you measure with EBSD on a microstructure, you can classify deformation structures or dislocation structures into two types. One is called statistically stored dislocations, and one is called geometrically necessary dislocations. Maybe you have heard that already, SSDs and GNDs. And here I have a picture to separate that a little bit. Imagine you have a lattice like that, and this lattice is connected to another lattice like that, and another lattice like that. And now we plot the dislocations inside which make the misorientation from this crystal to this crystal and to this crystal here. It's a bit bad drawing. In principle, this should be just also almost close to this one here. There should be a small angle grain boundary in between, and these dislocations make just a transition from one orientation to the other. These dislocations, and which are forming subgrain boundaries. And then we have another set of dislocations. You see them here. I have plotted them, but just ending lattice planes here. They are also more or less the same type of dislocations. They just make a rotation of the lattice from here to here. So the lattice slowly moves over from there to there by regular insertion of dislocations. So these dislocations all have the same Burgers vector. Yeah? They all have a Burgers vector which is pointing this way. Slightly inclined, but in principle all the same thing with respect to the lattice. So all these dislocations which make measurable crystal rotations, so a crystal rotation from here to here, a crystal rotation from here to here, and from here to here, these are called geometrically necessary dislocations, because if you anneal this material and it's not recrystallizing, these dislocations will stay inside and nothing will happen. Yeah? So they are measurable by EBSD, and we call them GNDs. Create measurable lattice rotations. Now you may, however, in this lattice here have dipoles of dislocations, and so dislocation dipoles, and you may have the same thing here, dipoles. Each, you have a plus and a minus dislocation, together is no rotation. Although there may be many of these dipoles, there may be a very large amount of stored dislocations. You will not see them with EBSD, at least not by a misorientation. Yeah? So as a result, these dislocation dipoles cannot be seen, and we call them just statistically stored dislocations. Yeah? So as SSDs, they actually, you can see them with EBSD, but they only lead to a blurring of the diffraction pattern, but not to measurable rotations. Okay, so this is an important the dislocations itself are not different. No? This dislocation is not different from this one, but the arrangement is different. No? These ones are in dipoles, and these ones are monopoles. No? So now we are using, actually I should tell you something disappointing. Many people think, if I measure with EBSD, I measure the GNDs, then I get an idea how much is the total dislocation density. And this is actually not true, because all these dipoles are usually much more numerous than the others. Usually we find that we have about 10 times more dislocations than we have GNDs. So this is a very often a typical finding. So if you measure GNDs, and I will anyway show you this now, then you are not getting the whole story of deformation. But because we have nothing else, we often go and do GND measurements. We can talk about that later as well. But, oh yeah, this is in principle what I just wanted to note. GNDs indicate only how much different is plastic flow in different areas of a grain. If you have a whole grain, and in this corner the crystal rotates like that, and in this corner the crystal rotates like that, in between you get GNDs, which are indicating that the crystal deformation is not homogeneous. So GNDs indicate the difference in plastic flow and not the total amount of plastic flow. Yeah? You could deform a crystal very much and not create any GNDs, yeah? If it's homogeneous. If it's heterogeneous, it's a different story. So now how can we measure them? How can we measure these GNDs, even knowing that this is a limited concept? Yeah? But it's nevertheless an interesting concept. We use in EBSD something which is called kernel average misorientation. Also, again, later on we'll talk more about that, but what does it mean? Imagine we have measured a very big map of EBSD, and each of these in this map consists of individual pixels. I see all the pixels in a very large map, but I take out only a kernel here. A kernel is one center point with all its neighbors around. Yeah? This could go on forever here, this plot of little hexagons. Each one is just one measurement. And now I do the following. I take the center point and I calculate the misorientation between the center point and its surrounding neighbor, and of the next one, and then I average all of these misorientations, and I obtain a value which is called the average misorientation in this kernel average misorientation, KAM. Good. And now very nice is that I can quantify this KAM in terms of dislocations. I can say, okay, I assume that here's one grain outside, and inside is another grain, and between this inside and the outside grain, I have the misorientation exactly equal to the average misorientation, the KAM. And from this assumption, I can calculate how many dislocations do I need to create this rotation from one crystal to the other. And that's what I'm doing. And in this way, I can, and here's the equation, it's very simple. And then what can I do? I can make an EBSD map, a very large EBSD map, and very large or very small, whatever you like. This is a large one, and now I calculate first the KAM. The software does this automatically. So I plot here my KAM value from 0 to 4 degree. Colors mean blue means no misorientation, and red means 4 degree local misorientation. And now I'm just taking this equation, and I'm changing the KAM meaning into dislocation density meaning. Yeah? So it's just linear. No? The dislocation density is directly proportional to KAM. So the rest is just factors from the measurement. And that means I can, instead of plotting this in form of KAM, I can plot it of GNDs, in terms of GNDs. This microstructure here has everything between 0 and 4 times 10 to the 15 per square meter dislocations. Okay, so now we have a nice measure of the amount of dislocations inside of a material. And we can use this now, for example, for the following beautiful thing. Now we come again to a materials example. We took, is it written here? No, it's not written, but we took a DP steel, dual phase steel, and we heated it up to 800 degree. At 800 degree, it's all perfectly austenitic. Oh no, it's not. It's austenitic ferritic, and we wait for a while, a couple minutes, and then we cool down and let the residual austenite transform into martensite actually, or into a magnetic structure. And we do this transformation here at around 600 to 500 degree at different temperatures, and we cool down, and then we look in the properties of this material. Yeah? And we find, surprisingly, just the hardness as an example of properties. If you cool down at 500 degree, if you transform at 500 degree, you get relatively soft material. And then at 580 degree, or 575, you get a maximum of the strength, and then it becomes soft again. So what happens? Why do we have this interesting behavior in material properties? So why do we have actually this peak and then this big drop here? And I just show you the two microstructures between this peak material and this cooled down at higher temperature transformed material. And these two, so yeah, that's important. We have only 25 Kelvin difference in holding temperature, but we get 15% difference in strength. So that's quite an amazing thing, and for the steel industry, certainly interesting whether it should go to 575 or 600 degree for holding, yeah, in order to gain 15% of strength. That's quite a good deal. So we look into these microstructures. This is 600 degree, and we have relatively large ferrite grains, free of any kind of dislocation. So this is a KAM map. We have few island grains of martensite, and we have relatively large grains. And now this is just 25 degree colder, completely different looking. We have now ferrite with the ferrite here has relatively high local misorientations. We see many smaller islands of relatively soft martensite, and we see smaller grain size. So which of these differences of grain size, dislocation densities, so KAM densities, martensite hard or soft, which of these differences is responsible for making this peak of the in strength? And this you can figure out by calculating now. So you take all these, you take EBSD. I said EBSD is a quantification technique. You quantify grain size, you quantify martensite grain size, you quantify martensite volume fraction, you quantify dislocation densities, and now you take all these numbers and you go into a calculation. So you say the hardness calculates out of hardness of martensite and ferrite, and the hardness of martensite depends on the carbon content. You can also calculate the carbon content, and then we consider the effect of grain boundaries by using a Hall-Petch relationship. We consider the dislocation density by using a Taylor equation, and finally we are bringing this all together, and we get an explanation for the strength of the faces of the material. We bring this all together in a big calculation scheme, and then we calculate. And so again, for our experiments, and these are the calculations, and we find out, okay, we do not get exactly, here was our measurement, and we do not yet completely explain our measurements, but we see that the peak is at the same place. We can reproduce the peak. We cannot reproduce the strong decrease of hardening here, and we know why. It's actually, we are considering only GNDs and not SSDs. Yeah, EBSD only allows us to measure the GND densities and not the total dislocation density. Therefore, we don't get this drop here, which would be a drop in SSDs, a very significant one. But we can reproduce this. And now we can do something very beautiful based on that. Let's switch over that. That's the measured hardness, and that's the calculated hardness. So it looks relatively similar, but not exactly identical. And now we can say, so which of these microstructural elements have contributed how much to that? So this one here is the contribution of martensite volume fraction and martensite hardness. This one here is the contribution of grain size, and this one here is the contribution of dislocation density. So, and if you add all these lines together, you get to this. And now you could say, okay, what would happen if I change the martensite volume fraction a little bit? Oh, start with GNDs. If I would change the dislocation density by a factor of 10, then we would get up to this place here. The hardness would rise up. And we can say 10 times makes this change. for an engineer, fantastic to know how much is the effect of it. How much would it be if I make the grains larger, yeah, or smaller? If I make them larger, the hardness would drop by that. What would happen if I change the martensite content? I only make 15% larger martensite, more martensite, and I get a surprising increase of strength. Yeah? And so altogether, this allows us now, without further explanations, to engineer microstructures, saying, is it good to go for smaller grains? Is it good to go for more dislocations? Is it good to go for more martensite? And from this, you get really a quantification just based on EBSD on how to handle your microstructures. Yeah? So this was, yes, please.
Sir, when we are calculating the GND contribution,
yes?
can we quantify that which type of dislocation will be differential, like edge dislocation, or because for not the edge can be high?
Yeah, okay. This is in principle, the answer is yes, we can calculate that. But here this would be too detailed calculation. It would take very long, and it would also not give us very much additional knowledge. But indeed, we are able to, I will come to that, I have only 2 days. If you give me 2 weeks, I come to that. How to calculate actually whether it's edge or screw dislocations. If you mean that, no? Whether we can separate into different sorts of dislocations, we can do that. It's quite a complicated calculation, and at the end, it doesn't help us here very much. Here it would only help us to know what is the total amount of dislocations. That's a quick calculation, yeah. And but you can do that, and for other questions, it's interesting and important to know. But this is a quite complicated tensor calculation, which I will not address right now, at least. Yeah. Mm-hmm. So what is that now? Okay, ready with EBSD, with my introduction to the introduction of EBSD. Yeah, I have given you a couple of examples. I could give you many more, for example, about resolution of EBSD using TKD and so on. But let me wrap up what we learned on EBSD so far. Certainly you see how versatile is EBSD, yeah? That it allows us to look on many different materials, many different questions. It solves us a lot of material science questions. It's quite nice. And I would like to point out the data are accurate and they are quantitative. It's not just a picture. You get really numbers, and that makes it so superior to other microscopic techniques where you just get pictures and you have to infer from that. No? And this allows us to look on textures, microstructures, crystal structures, grain boundaries, and so on. Very many materials are accessible, and I should not forget, we have an ever-increasing spatial and angular resolution. So the spatial resolution particularly is a limit, but we are getting better and better with modern techniques, with modern microscopes, modern detectors. I could speak about that as well later on. Direct detection is, for example, a big issue currently. Dictionary indexing could be very nice. Cross-correlation you will see in a moment. Okay, then we have this possibility to correlate EBSD with many other different techniques. EDS, CL, TEM, APT, nano-indentation, and name it. There's many different possibilities. It's a very flexible technique. And you have seen 3D. It's kind of an exotic technique, yeah, the 3D EBSD. We are mostly relying on 2D, but once you have 3D, it opens, of course, still a new world. Yeah? Yes, and then not only you can combine EBSD with other techniques, but you can also combine it beautifully with modeling techniques. Yeah? That means, for example, with crystal plasticity, with phase field modeling, with POTS modeling, molecular dynamics, and whatever. Always possible to understand processes going on which you cannot directly observe. Yeah? So that's, I think, a really beautiful and powerful technique, and still not explored to the end. And now I would like to show you how we can combine it with ECCI. So this will be still, I apologize, I think until 12:30 you have still to persist here, no? Or maybe even a little bit longer. All right, good. So the limitations I mentioned already. Spatial resolution is a limitation. Angular resolution is a limitation. I could speak about that a little bit in more details. I just say here the correct determination of the pattern center is one of the biggest pending issues in this angular resolution issue. If we can solve that, and you will understand hopefully later on what is that exactly, what is that problem, then we could actually do residual stress measurements as we can do it with X-rays, but anywhere in the microstructure. That would be a dream, I think, for many material scientists. Yeah? But this is a big issue, which is not solved yet. Sensitive materials, for example, you have materials which are, once you have put your electron beam on it, whoops, the material is already destroyed. Yeah? I have worked on solar cell materials which are very sensitive to the electron beam, and there we need new techniques, new EBSD techniques which allow to go with this. There is techniques in the then in situ observations. Of course, in situ is beautiful, you see a grain growing, you see a grain deforming, but one always needs to take into account, keep in mind that you are looking only on the surface. And the surface, particularly for thermal processes, are very often not representative of what happens inside of a material. Just imagine you have a nucleus of recrystallization which is at the surface of a material and wants to grow. It is, however, of course, it is cut. The nucleus structure is destroyed. So the nucleus on a surface will behave very different from a nucleus inside of a material undestroyed. Yeah? So if you make conclusions out of a 2D in situ observation, then also imagine a deformation experiment. You have no stress on the free surface. Yeah? It's very different from a stress from a constrained sample, from a constrained grain inside of the material. So if you want to make conclusions from that, you must be very careful. 2D, it's only 2D observations with respect to 3D bulk. And if you want to go for 3D, then unfortunately you cannot do in situ because 3D is a destructive technique. So you're kind of in a dilemma, yeah? Which can only be solved by adding maybe modeling techniques to that. And then, yes, last but not least, sample preparation is also quite an issue. You asked for ceramic materials. Particularly there, you have charging materials, you have many different phases, how to handle materials which charge or which are sensitive, how to create that. Yeah? But also in metals, you have multi-phase materials. One phase is soft, the other one is hard. One is quickly dissolving, the other one is not dissolving. Sample preparation can be the most challenging problem of making nice EBSD. Yeah? And before you do a proper EBSD measurement, I always recommend stay a couple weeks in the lab, not weeks, months, I mean, yeah, and make a nice sample before that. No? Okay, that was a joke. I hope it doesn't take months. No? But it indeed, sometimes it takes months to get a good sample. Yeah? And then you get rewarded after that only. Okay, so now we come to ECCI. Sorry. And I start with, again, an intuitive introduction to why we see electron channeling contrast. And then I show you two examples to illustrate the power of that technique. Oh yes, and this is my most preferred motivation. To show that everyone who is doing TEM is betting on the wrong horse. Yeah? No, don't believe that one. No? That was a joke again. And if there is a serious TEM person here in the room, you may throw now rotten tomatoes on me. Is there? Yeah. Okay, sorry for that. But I like to, I tell you this little story. When I first went to conferences with the ECCI and the physical description of ECCI, and a TEM person listened to me and said, suddenly you SEM guys are also dealing with Bloch waves. Why that? Yeah? And I said, because we're doing exactly the same thing as you, and we're understanding it like you as well. No? And they were a little bit disappointed that the SEM people come and wilder on their ground. Yeah? But we do more and more. Good. Okay, but you will see it's a beautiful technique. I like it really very much. So, and I introduce it with the following little comparison. And my TEM work I have taken from literature, from a paper actually. And this is actually a TEM paper, a beautiful paper on nano indentation in a strontium titanate. Yeah? I always say strontium titanate is a sample which is built in by standard into every TEM which you buy new, because everyone who presents pictures of new TEMs is presenting strontium titanate. No? And I wonder, okay, do you get a standard sample with, okay, this is again a bashing of microscope, TEM bashing, which I do not want to. But this is really a nice work. So you have here a bicrystal. Here's a grain boundary. Here's one crystal. Here's another crystal. Here is an indentation tip, an indenter tip, which is now pressed into the sample. And you can observe in situ, more or less, what the indentation is doing. And this experiment is very demanding. This is a beautiful experiment. I'm certain they have worked for months on this experiment to get a proper bicrystal with the right two crystals, nicely oriented with respect to the indenter, then the indenter coming right straight onto this thing here and having the sample is not falling down, it's not breaking, and everything beautiful. And what you can see then is when you start indenting, you see dislocations piling up against this grain boundary, and after a while you see the dislocations get denser and denser while we are indenting here, and after a while you get a pop in, and then dislocations are forming everywhere, and you get a big pile up of dislocations here. Still no transmission into the neighboring grain. Yeah? But this experiment is very nice and teaches us a lot of things, but it's probably one out of very few experiments which was successful. And now we cannot do the same thing with ECCI, because currently I don't see yet a proper way to see dislocation evolution in situ. Because while the indenter is there, you cannot look onto the microstructure. Well, there's maybe possibilities, but currently not. At least I have not explored. But what you can do is you can indent and then withdraw the indenter and look on. So you indent into a bulk sample. You don't take a thin foil. You just take a nicely prepared sample. You indent. And then so this was a 50 nanometer deep indentation, and then you look on all the dislocations which have formed when you do 50 nanometer indentation. Then you can go and make an indent here next to it, 100 nanometer indentation or 25 nanometer more. You can do all these kind of experiments a little bit off situ, but or ex situ. But nevertheless, you can see very beautifully in a SEM all the dislocation structures forming here. Yeah? Here's one source emitting dislocations. Here's another source emitting dislocations. This one here is stacking faults, which actually, here's a partial dislocation, here's a partial dislocation. Between them is a stacking fault. And if you look on my computer, you see actually the thickness fringes as you would see them in a TEM as well. So it's the same picture as in a TEM, just from a bulk and not from a thin foil. And these stacking faults, they come from a slip system which has been activated deep below the indent, and then they come out under a certain angle, and they come at a distance of 400 nanometer to the center, they come out to the surface. Yeah? And all this you can see very nicely, and this is an experiment which just takes a few minutes to make it proper. And then you can go and say, now I can make this experiment not only on one grain, but on 100 grains, on all different kinds of orientations, which I measure with EBSD before. Each time I make here a map of 5x5 indents, so I get statistics. I can say, okay, I get lots of these dislocation structures, and by looking on 25 indents into the same grain, I can tell what of this is stochastic behavior and what is systematic behavior. Yeah? So I can explore the systematics of deformation with this experiment. And I can do it in different grains, in different phases. I could go to a grain boundary and do it there and see how dislocations transmit into the neighboring grain. But what I did here is I took these indents into 20, 30 grains. Then I took all these pictures. Then I polished the sample very lightly to remove all these indents. I charged the sample with hydrogen, and I indented the same grains again. It's exactly the same grains, and I compared. And what I did, I selected, for this presentation, I selected just 4 grains. One grain which has an indentation direction here, another one here, another one here, and a third one here. And each one, you see very characteristic dislocation systems being formed. Yeah? Of course, you see the symmetry of indentation, but you also see how many dislocations are excited and how dense they are and so on. You see a lot of information. And then I polished and charged the same thing with hydrogen and look I looked into exactly the same crystals again. So this before, and this is after hydrogen charging. So this is without hydrogen, and this is with hydrogen. And now I compare the densities and the splitting of the dislocations, and I understand a lot of the effect of hydrogen on this material. Yeah? And you see here these beautiful dislocations coming out of one source here, and now I can see, is this the same amount of sources activated? Is it the same distance between the dislocations activated? I have all kinds of possibilities to see things which you usually can only see on a TEM, but to see it in an SEM on a bulk material. Yeah? So that's in principle the power of that technique. Oops, so this is, let's not go into details, but let's look why we see something. Yeah? Why do we see the same thing as in TEM in an SEM? Why the hell is that? Why don't I go to TEM any longer? Yeah? So the thing is, you just need to understand diffraction. You solve the Schrödinger equation again, and what you get then when you solve the Schrödinger equation for an electron traveling into a crystal lattice is you're finding a wave of electron intensity or of electron density traveling through the material here. Or actually it's a standing wave, and depending on what is the direction of the ingoing beam, the standing wave has a different distribution in the lattice. Yeah? There are areas where you have minima of density, that means there the charge density is low, and there are areas where you have maxima of this charge density. That you could say there are many electrons, but what is an electron? We don't know what is an electron. No? We just know it's a charge density there. No? Something happens there, and it happens particularly when there's many, and not very strong when there's minimum. Okay, and now you see that this obviously depends on the direction of the primary electron beam with respect to the lattice. And I can tell you already, when the electron beam just hits exactly in the Bragg direction, then we see a particular distribution of electrons inside. Yeah? Good. And in TEM, we would now, under certain directions, we would get a resulting electron wave out, and we call this diffraction. We simply call it, when we are in Bragg diffraction, when we are in Bragg angle here, then we will see very low, very strong resulting beam here, and then we call this Bragg diffraction, two-beam Bragg diffraction. So that's clear, everyone knows. Now, how do we see now something in backscattering? So, of course, we have an infinite sample. We cannot look below here. We can only look from the top. So, actually, what you have to consider is that these electrons, which are spreading through the sample, through the crystal, through the atomic structures, they are interacting with the atoms. And they are not only doing Rutherford interaction, that means elastic interaction, which leads to diffraction, but they are also doing inelastic interaction. That means sometimes they hit a nucleus and are backscattered to the sample. And the amount of backscattering is depending on how many electrons are at which place. So if there is a maximum of electrons at the nucleus, we will get a lot of backscattering, and if there is a minimum, then we will get no backscattering. And when there is a minimum, we will get strong diffraction and no backscattering here. Yeah? And if it's inverse, then we'll get no diffraction and strong backscattering there. Yeah? So we'll actually see here just the inverse of what we see here. It's just the same thing. We're just getting electron diffraction. We are just calling it different. We call it channeling, but it's in principle the same as TEM, just the contrast is inverted. Yeah? Something which appears bright here is dark here, and vice versa. So that's in principle the whole story. And there is more to know, but not for today. Now imagine we have a defect in there. Let's say this is a block with one dislocation line here inside, and this is a picture of this dislocation line, cross-sectioned here somewhere, yeah, in the middle of this 3D block. The dislocation line, and what is a dislocation line, is just an additional lattice plane. So you see here below the dislocation, this lattice plane is missing, and as a result, we have here a perfect crystal, and here we have a perfect crystal, but with one line missing, with one plane missing. So now we put our electron beam on, we select it such that it will be in channeling conditions, so in Bragg diffraction condition for the perfect crystal. And what happens now when we come to the dislocation? Here, there is one lattice plane missing, so it's no longer in Bragg condition. It's actually the lattice, no, the waves here are actually shifted by half a lattice plane, and instead of having perfect backscattering, perfect channeling, they have suddenly perfect backscattering. So as a result, we will see this part here, this area, we will see as a strong white signal on an otherwise black background. Yeah, so if we look then from the top, we will see the dislocation as a white line on an otherwise black area. And of course, where the dislocation comes to the surface, the signal is strongest, and the deeper it is below the surface, the weaker it is. So we see in principle such a picture. And that is a typical picture from a high entropy alloy, which actually shows a lot of very interesting features. So first, if I would not tell you this is an ECCI image, you could also guess, this is probably a TEM image. Yeah? So what you see here is all the dislocations here. They are gliding on different slip planes, actually very, very dense planar slip, obviously. And if you look, for example, these dislocations, this one here is a typical example, they show this funny oscillation contrast. Bright, dark, bright, dark, bright, dark. Typical for TEM images as well, and appears due to the fact that this dislocation is not parallel to the surface, but inclined with respect to the surface. You see it here as well, you see it here as well. What you also see is here, if we zoom in there, you see the dislocations are grouped, always in pairs. Yeah? And they have this typical oscillation. It's going this way, and you see always grouping in two. And this grouping in two could have two meanings. One could be that this is a dislocation dipole. So you have a plus dislocation and a minus dislocation, and they are coupled together. So this one would be plus, this one would be minus. But it could also be that these dislocations are of the same character, and they are just grouping together because they are destroying a short-range order. So one dislocation is destroying it, and the other one is repairing it again. So that could be as well the case. So, and actually, in TEM, it's very difficult to distinguish between a plus and a minus dislocation. But here in ECCI, actually, we have a quite easy tool because we are seeing the details of this dislocation oscillation, and we can calculate from that the Burgers vector. And, oh yeah, I'm coming to this in the next slide. Just shortly give me an indication what you need to make this beautiful ECCI. You need, like in TEM, you need a parallel illumination. Usually in an SEM you're using convergent illumination. You need here parallel illumination, which is not so nice because when you have parallel illumination your spot becomes wider. So you want a small spot size at the same time, parallel and small. This is difficult to organize. And you want it at high beam current because this is a relatively weak technique. So it needs a lot of power. And finally you need a sensitive and a quick BSE detector. I always say this is kind of contradicting demands, and a particular sort of microscopes is actually most suited, and I don't get any money from Zeiss for saying it here, but it is unfortunately a fact that Zeiss microscopes currently do it best because they have a very particular optics. Yeah? And then JL microscopes have started to build in a special optics as well in order to do that. All other microscopes don't do this very well. No? But Zeiss, I should ask for money from Zeiss for making here advertisement, yeah? In front of so many young engineers buying many microscopes in the future. No? I will ask them, yeah. No, but what I also should not forget, this is all microscope thing, but one more thing is missing, and that is a good operator who knows to do that. That means you need me. You need me as well. Yeah. So you buy me together with the microscope, I come. All right. Good. That's a little joke again. But let me show you now. Coming back to this picture, how can we understand whether these dislocations are dipoles or two following monopoles? And for that, we have recently done calculations of this intensity, of this dislocation intensity, and we do this in collaboration with Marc de Graaf in Pittsburgh at Carnegie Mellon University. He has special software, EMSoft, which allows that. And we calculate for these dislocations the appearance of these dislocations. And actually, now let's not take too much time, but you see if we take a positive or a negative Burgers vector, you see that the oscillations invert. One oscillates up, down, up, down, up, down, and one oscillates down, up, down, up, down, up. Yeah, and we see that for all these features here. If you look a little bit more in detail, you see it clearer. And from these calculations, we are now able to understand, is this the same type of Burgers vector or is it dipoles? Yeah. And this is actually a very beautiful application of understanding this microstructure. This was metals, and now for the only time in my presentation here, I will come to a non-metallic material, and that's actually pyrite, because the question was, does this work only on metals, or is it also possible to do on minerals, on ceramics, and so on? And indeed it is. We have done it on quartz, we have done it on feldspar even, and we have done it here on pyrite as well. Pyrite is a relatively, it's still cubic, but for a metallurgist, a relatively complicated crystal structure, which is consisting, actually, it's a sodium chloride unit cell. So sodium, sodium chloride, chlorine, sodium, chlorine, and so on. And instead of the chlorine, you have a dumbbell of sulfur sitting there. So this is in principle the crystal structure. And this crystal structure, the question was, can we understand how this material deforms when it is in the Earth's crust and it's pressed in the rocks? How does it deform? And from this, can we learn how the material rotates and whatever? And for this, you need to know what kind of potential slip systems are there. And this is more complicated than in metals. It can deform on the cube systems. It can deform on the diagonal slip systems. It can deform on these ones here, double diagonals. And it can also have this combination. So there's a lot of possibilities, which is all unknown. And we took ECCI. This is one of our, I think, very beautiful ECCI images of this material. And you see a whole wealth of information in this material here. And let me work through it very shortly only. So this is the orientation of the crystal. This is the diffraction pattern, which is responsible for creating this picture here. So the O2O reflector is excited currently, but that doesn't matter for the moment. Let me just show you a few features, not explaining more. So you see first these dislocations here. If we zoom in, they always have a white side and a dark side and a white side. And like that you can actually separate. And actually you can, by calculation, show that the Burgers vector is then parallel to or perpendicular to the contrast change from white to black. And we know what kind of direction is there. We know that it's a 101 direction, so we can tell what kind of Burgers vector we have there. Then we have this feature here, these little ones, green. They are, that's difficult, not yet understood. They have a black-white contrast and then this tail here. Always black-white and the tail. We imagine that this is an inclined 110 slip system. Yeah. Then we have these ones here. This is super interesting, this one here. You see white-black, black-white, coupled close together. So is it better visible there? I don't know. But this is a dislocation dipole of a plus and a minus dislocation. Yeah. And then we have all kinds of stacking faults. This yellow ones, blue ones, red ones, and they all have very typical differences in their contrast. One is white-black, one is black-white, one is white only, one is black only, and all of these we can analyze with crystallographic knowledge. We get it all out of that. So it's, you see how powerful that is. So what have we observed? We have worked on metals. So to wrap up a little bit, and then I show you one example or two. ECCI goes extremely well. It goes super on superalloys. I think that's the name for why it's called superalloys. Yeah? It goes very well on steels, both BCC and FCC. It goes not so well on aluminium alloys, or it depends on which aluminium alloy you're looking on. Magnesium alloys, I'm very sorry for my current Indian PhD student who fought for 3 years to get ECCI on magnesium alloys and still comes out with only 3 images, 1 per year. No, but he got a lot of beautiful, you know his work, now Supriyo Nandi. He has tried on magnesium alloys to do ECCI. It's a challenge, and I could tell you why. Titanium alloys go well. We have done on semiconductors. Gallium nitride gives beautiful pictures. Also, cadmium telluride, for example. Silicon is more difficult because, like magnesium, it's very light. It scatters very badly. Ceramics, we have looked on strontium titanate. More I have not yet seen, but I have looked in minerals. We looked in oxides of magnesium and iron. We looked in pyrite. We looked in quartz and some others. And it works everywhere quite decently. Yes, and what can it do actually? So clear. You have seen it's giving TEM-like characterization of defects, of dislocations and stacking faults and nanotwins and even strain fields, but not on thin foils, but with bulk samples. This is a big advantage. And of course, this allows us to see things in a more natural arrangement. Yeah? In a thin foil, when you make the thin foil, often the sample starts to releasing stresses, which you do not have in a bulk material. You can do very nice in situ experiments because you're keeping a bulk sample. You can look on dislocation densities up to the 10 to the 14, and for dislocation densities higher than that, you can use eBSD quite nicely. And here's a table with comparison. Of course, in lateral resolution, we are not as good as a TEM. For classical TEM, diffraction-based TEM, we have maybe 1 nanometer resolution for dislocations. Here we have about 10. The depth of observation, so how deep in the sample do we look? This is on a TEM foil. It's usually in the order of 100, maybe 200 nanometer. Here we see approximately the same depth. Of course, the observable area is orders of magnitude bigger because we have just a bulk sample. And good, that's bulk sample versus thin foils. I have published this together with Nahid Elhami in 2014 already now. And I still think this is quite a valuable paper. It's an overview paper of 30 pages. If you like to learn more, that's, many things are in this paper. Okay, I just take a drop of water and then I stress you for the last 15 minutes. Okay. One thing, let me see what really comes. Yeah, okay. When you do ECCI on a material which has been fatigued, so we actually did a fatigue experiment inside of the microscope. You have a little fatigue, a little tensile compression test sample inside of the microscope, and you can move it and you can see how these dislocation structures work, form. In fatigue, it's well known that after 100 cycles already, the dislocations start arranging in very dense arrangements without almost no dislocations in the channels and heavy dislocation densities in the walls. And these dislocations which are in the walls, they consist of dislocations of two types. On one side they come from one side, and on the other side they come with a different sign. So you will see different rotations on either side of these walls if you do eBSD across it. And you will also find that in the middle of that wall, the residual stresses get very high. So there's quite a complex arrangement of stresses and strains inside of such fatigued structures. And we want not only to see with, this is an ECCI image, and you will see later we can really see every individual dislocation in here. But for the moment, let me just explain how do we get information about stresses. We use a particular eBSD-based technique, which is called cross-correlation eBSD. And I just have a very simple graph to show you how this works. So we take a diffraction pattern from this area here, and we take a diffraction pattern from an area which we want to measure. So from which we want to know the residual stresses. This one here has been taken in an area where there's nothing happening. So we assume there is no stress. We take this as a reference. And this one is an area where we assume something has happened. And if we go and compare these two, we see that due to the elastic stresses, which are the elastic strains, which are residing here, we see a change of the diffraction pattern. Yeah. So and now we put these two patterns next to each other, one from that side and one from that side, and we compare pixel by pixel how is this pattern changed with respect to this one here. So we actually make little areas, and for every area we calculate how has this area been shifted relative to this reference area. And we draw this shift in form of a little vector into each of these regions of interest. And you find in this case maybe it has been just strained in both directions here. So there's probably a linear expansion here. And now from all these vectors Q, you're able to calculate what is the stress situation, what is the elastic strain first at that place which we are measuring relative to this place here. And we can then obtain from this the displacement gradient tensor, and from the displacement gradient tensor we can calculate the elastic stretches, which is the symmetric part of this tensor, and then of course the elastic stresses using just the stress equation here, and then from the crystal rotations we can get from the antisymmetric part of this tensor. So applying that, we are able now to plot the stress and strain distribution with a decent accuracy, and here you see it. So this is the distribution of the von Mises stress. This is the distribution of the rotations, or displayed this time as G and D densities. I mentioned G and Ds already, and you can now go and distribute. Oh, this was your question, or was it yours? I don't remember. Can I distinguish different slip systems? Can I distinguish between different sorts of dislocation, screw and edge, for example? And indeed, yes, you can here. When you have these detailed calculations, you can say, okay, in these areas here where we have the dislocation densities, we can show that there is a particular sort of edge dislocations, and at every other places there's a particular sort of screw dislocations, and so on. So we are able to calculate that, and we can then combine ECCI and this cross-correlation EBSD measurements. And here you see with ECCI, you see all the little stacking faults with dislocations being split up, and you see all the individual very dense dislocations, and we can calculate from this the dislocation density. How high is it? I don't remember. The total dislocation density is just 10 to the 15, and the G and D density which we calculate is an order of magnitude smaller, 10 to the 14, and that means 10 times difference, yeah? And we are able now to calculate that the G and D densities are very high here and here, and the stresses are very high here in the middle. G and D density in the middle is low, it's actually only SSDs, but here, right and left, we have very high amount of G and Ds, so we get a very complex picture of the construction of these fatigue walls, yeah? And we published this recently in the Journal of Plasticity. We learned how fatigue plasticity proceeds here. There's two papers, one on the effect of hydrogen on this one, and one just on the formation of these walls. With Daeyong An was my PhD student on that. I think a very great work he did there. Fantastic work. Okay, and then the last moment, and then we are ready. If you now look on these structures without hydrogen, you saw it just before, and with hydrogen, same magnification, I think, and the same, more or less the same crystallographic direction, 315, 314, and you see actually these walls here are very dense, very many dislocations squeezed together, while here this is much looser, there's much less dislocations in the walls. Yeah? So with hydrogen we have much less density of dislocations than without. So you see here it's 10 to the 15, and here it's 2 times 10 to the 14, so about 5 times less dislocation density there. And this is not only one observation, we have made many observations, this is always like that. Okay, this is just how we calculate the dislocation densities, and so the dislocation density in the walls is reduced, and that shows, what did it show actually? It's a bit difficult to explain what is exactly written here. I need to go through this step by step to explain you why this is lower, but there is a clear indication that hydrogen is responsible for this low density. And from that, then we continued fatiguing with hydrogen. When you do it without hydrogen, you can go 1,000 cycles and nothing happens. When you do fatigue with hydrogen, and you do only 5 fatigue cycles, you see the first cracks opening. Immediately, with hydrogen, the thing becomes so extremely brittle that immediately the material cracks, and you see it here actually, all these white lines is actually epsilon martensite, which forms much more severely when you have hydrogen in the material than if you don't have. And everywhere where, where this epsilon martensite ends up on the grain boundary, you get severe cracking. And we were now able to explain with our ECCI and EBSD combination, okay, I expected a picture to come. Why not? Maybe I dropped it out this morning in a sleepy mode. Yeah, obviously I did. Now, then it comes later. Then it gives me the chance just to summarize. So, but let me show just this picture here once again. Oops, too quick. We could explain why, particularly at these areas where epsilon martensite hits the grain boundary, why we get this very early fracture, this early cracking. And it's actually a number of reasons. One is, when the epsilon martensite arrives here, it shears the lattice locally very strongly, because epsilon martensite is a shear formation. The second is, epsilon martensite forms out of dislocations moving. Yeah? Each partial dislocation makes an epsilon layer, and each partial dislocation transports hydrogen out of the material to this area, to the grain boundary. So it embrittles the grain boundaries additionally to the high strain which we have there. And so this leads to very quickly to the formation of these stresses, of these cracks. Okay, this was the final example, and now I just wrap up. You have seen we have two techniques which are both diffraction techniques in the SEM, and they are both applied to large and bulk samples, and they are very complementary techniques. Yeah? You don't need a cinfoil, you don't need any special sample but a nicely prepared surface. Then you get, because you're working on very large samples, or you can work on large samples, you get very good statistics. You don't only have one little grain boundary like in APT, yeah, where you get miserable statistics. Okay, little joke, but indeed here statistics can be very good, and statistics matters very much. If you want to understand really materials with a good confidence, yes, that what I see here microstructurally is responsible for the properties, then you need to deal with statistics. It's quite an important thing. You get, nevertheless, reasonable good spatial resolution. With EBSD, we have spoken, quantitative microstructure, large areas, okay, in situ possible, and so on. Limitations, I mentioned, spatial resolution. And with ECCI, you have, as a complementarity, you can see, here you see the defects only indirectly, by rotations. Here you see the defects really directly, like you do it in TEM. And again, here, with respect to TEM, lateral resolution is, of course, a limiting factor. When dislocations get too dense, you can't see them. There is resolution images for certain. And particularly on light materials, I still haven't figured out what are the best conditions if you're working on magnesium or on silicon or so. Probably dropping the voltage and going for lower acceleration, for lower energy of the electrons helps. It does help, but we're not yet very confident that it is really an easy technique in this case here. Yeah, that's it. I have stressed you enough for the morning. Thank you for listening. Yeah. Mm.
So if you have any quick questions, one or two we can.
Yeah, I'm still.
You're not tired.
No, I'm not tired, but you are tired, I think.
No, definitely not. I think your last image was picture perfect. Looks like a graphics, not like a.
Which,
last image looked like a graphic image.
you mean the which?
Epsilon martensite.
Yeah, the epsilon martensite. Yes. It's if this one you mean, yeah. I can entertain you with more of that if you want. We have the whole PhD thesis of Dayong An is dealing with that. Beautiful work. I'm really very big fan of this work. Yeah, Dayong was a good job.
This martensite in this the grain in the left
Yeah.
and the right.
Yes.
They are almost in the same directions.
You mean this one here?
Connected.
No, they are not. No. You mean here and here? By chance, I think the 001 planes are similar, but indeed, or the 111 planes actually in the austenites, you have some which are relatively similar, but the misorientation is 15 degree. So it's not so similar actually. Right? It's a large angle grain boundary, and here it's even 34 degree, and still the structure looks for alignment of 1-1-1 planes, yeah, because you once create an epsilon martensite on a 1-1-1 plane, and in the neighboring grain you want to continue with this deformation, yeah.
So this equation at the boundary ahead of the epsilon.
This one here?
Martensite,
Yeah.
each martensite. So you are saying it is because of the hydrogen.
This cracking, you mean?
Yeah, cracking.
Yes, this, when you have no hydrogen, there's no cracking. Now, of course, there's also then much less epsilon martensite.
Yeah.
So the epsilon martensite is important for the cracking, but I expected I would have another graph, but I have it later, I think on Friday. I have a graph, and I can show you this, show you this, to show you how complex is the martensite, the hydrogen interaction. Wait. Yeah. Euromud. This one here. I think here. This is one here. So the whole thing works like that. It's quite an amazing thing which came out of this PhD thesis. So hydrogen embrittlement mechanism during plastic loading of these. Actually, it was manganese steels. I forgot to mention that, but it's important. So first we have hydrogen inside. Hydrogen concentrates on the grain boundaries. This is our current work to prove with atom probe that the hydrogen is really where we claim it. We have only indirect proofs, and now Hina Kanchandani has the unfortunate Dr. Thesis theme to show where is the hydrogen really. No? So it's in the beginning, it's on the grain boundaries, but also everywhere in the volume. Now, the presence of hydrogen leads to a reduction of the stacking fault energy. And as an effect, as a result of that is, all dislocations start splitting up into partials. So you get stacking faults with partial dislocations, formation of stacking faults. This leads now to the Suzuki effect. That means the hydrogen likes to go into these partials because that's, actually it finds a better surrounding there. So the dislocation split up even more. We get very long elongated stacking faults. Now the Suzuki effect together with hydrogen leads now to the stabilization of the epsilon phase. So out of these stacking faults we are forming epsilon martensite. And this epsilon martensite now, because we have a back and forth movement during fatigue, it continues to transport hydrogen to the grain boundaries. So we get and the hydrogen then goes into the strain field of the epsilon martensite and collects there. So we are getting hydrogen in these strain fields of the martensite, and that leads then to hydrogen enhanced decohesion. So the grain boundary becomes weak and breaks up. Yeah? And so finally, we also have a cleaning of the microstructure from by the dislocation, so we get an additional hydrogen embrittlement by the help effect, by hydrogen enhanced local plasticity. So all this comes together. Suzuki effect, reduction of stacking fault energy, stabilization of epsilon phase, Heady effect, help effect, everything together to make this embrittlement. It's rather complex actually. Yeah? And the combination of all our techniques allowed us to prove that, except a direct proof that hydrogen is really there. And that is missing, of course. Hydrogen is so difficult to see.
Can do it?
In principle, yes, but only in principle. In practice, not yet. In principle, yes, because hydrogen gives a signal. Yeah. In practice, not, because actually everywhere in an atom probe you have hydrogen, and the hydrogen is so mobile it can go everywhere. Yeah. So we are currently trying to freeze in the hydrogen from the preparation on, and then so we charge the sample, maybe even when it is already a tip, and then we look where's the hydrogen going, and we try also to do this with deuterium instead of hydrogen, so we get a clearer proof of a clearer distinction between hydrogen which was in the sample and hydrogen which was already in the microscope. Yeah. So we're trying a number of things. Not yet with success, but this is also only half a year of Dr. Thesis so far. Yeah.
Okay, so let's stop here. Very good.
Yeah.
This one here.
Also, yeah, okay, right.
How can we use the cross-correlation technique that you mentioned for calculating strain across phase boundaries or grain boundaries?
Oh, this is not possible. No. You can, but this is a very good question. For the cross correlation, you always need a reference pattern. And this reference pattern must be almost identical to the measured pattern. Yeah, that means if you have a grain boundary in between, the pattern looks completely different. And you can no longer do any cross correlation. So you can only do cross correlation of an area close to the grain boundary with a place inside of that same grain. Of course, that's what we did here. Maybe that's what you actually mean. When I have the picture here. Yes. So here, this is the epsilon martensite, and we measured what are the stresses at the grain boundary here. But we can only relate a point at the grain boundary with a point here inside of that same grain. Yeah, we cannot say what is it across. The other side of the grain would have been measured with respect to another reference point in another grain. And if you have a phase boundary, again, you must have as a reference point a point in the second phase and in the first phase. Across that, there is no possibility because you don't have an absolute measure. You have only a relative measure of residual stresses. And that would be nice to have an absolute measure. And that's failing by the fact that we are not accurate enough with finding where is the pattern center of the EBSD pattern. So currently, yes, you can go to a grain boundary, but not across the grain boundary, yeah, with these measurements. There was also, yeah. Yes, right, yeah.
Dipoles can be distinguished in GBM. If we go from pluses to minus, yes.
Yes, I know.
Separation between them is
Yes.
that way we can differentiate.
I know, I am aware of that, of course. But it's a relatively complicated experiment. You need to carefully tilt, but I agree, this is possible, of course. And sure. Yeah. Yes, I'm aware of it, you are right. I just wanted to do a little bit of TEM bashing. No, I just wanted to proudly show that we can do it in ECCI as well, surprisingly. And I said it's more difficult in TM. It's maybe not true.
The main advantage of TM is that in the bulk sample, we can look at effects when we look at TEM.
Yeah.
Most of the time, that's what is dependent on our stress levels.
Yes.
That's the data.
Yes, right. Okay, correct. Yeah, right.
Okay, so let's stop here. We'll be back at 2 o'clock.
2 o'clock. Okay,
Yeah.
great.
For those, I think.